Hello everyone, and thank you for joining us today for the College of Engineering's 2026 Faculty Lecture Series. The series features faculty members who are leading cutting-edge research in climate science and related solutions, with a focus on understanding the complex processes underlying our climate, developing new technologies for mitigating climate-changing factors, and adapting to new climate conditions. Today's lecture is titled, Burning Truths, How Mass Timber Actually Performs in Fire. The lecture will be presented by Dr. Erica Fischer, the Glenn Willis Holcomb Professor in Structural Engineering. With that, it's now my pleasure to introduce Jack Istok, head of the School of Civil and Construction Engineering, who will introduce today's lecturer.
I'm pleased to introduce today's faculty speaker, Dr. Erica Fischer. Erica is the Glenn Willis Holcomb Professor in Structural Engineering in the School of Civil and Construction Engineering. Erica's research uses innovative approaches to enhance the resilience and robustness of structural systems affected by natural and man-made hazards such as wildfires, earthquakes, and more. Her work includes performance-based design approaches of structural systems, especially steel and composite systems, and their connectors. Erica's research is implemented through both large-scale experimental testing and numerical modeling, with the overall goal of reducing the environmental impact of the built environment on the natural environment. Erica, thank you for joining us today, and I'll turn things over to you.
Hi, everyone. Thank you so much, Charlotte, and thank you, Jack. Thank you to the College of Engineering for hosting me here today. I'm going to talk today about some ongoing research that we are doing here at Oregon State University on the behavior of mass timber in fire. This is ongoing research in collaboration with many other agencies throughout the country. You can see a little bit more about our project here at this website, but this project is really in collaboration with the U.S. Forest Service, specifically the Forest Products Laboratory and Northern Research Station, AREP, and the Environmental Protection Agency. It's funded through USDA, NEFA, and ARS through the Tallwood Design Institute, and it was supported by a lot of our industry partners, as you can see on the screen. All of the tests that I'm going to describe today were performed at the Bureau of Alcohol, Tobacco, and Firearms. We worked collaboratively with a number of different researchers in all of these agencies. And I want to make sure that they get all of the incredible credit for the work that they are doing. Despite all of the hard work that we're doing, we had a lot of fun doing this type of work. I'm showing some of our activities on the screen here, working at the ATF lab, doing our measurements and sampling, as well as featuring some of the students that have been working on this project quite tiresomely throughout the last few years. So today, what I'm going to do is I'm going to kind of cover a slew of motivations for this research. How did we get here? Why are we burning these timber compartments down? And what are we trying to learn from there? What is there to learn in the future? I'm going to talk a little bit about what we know so far in the fire field and how we can build upon that, decades and a century worth of research. And then I'll wrap up with what we did specifically, what we were testing and what we have learned so far and what we're going to be doing in the future. Okay, so a lot of our motivation for this project really lies in the incredible buildings that are being built out of mass timber throughout the United States. Here I'm showing the awesome Portland International Airport. This is a picture I took when I came off the plane and finally got to see the renovations at the Portland Airport. It's really quite magnificent as you walk into this big atrium. And a lot of different buildings are being built in a similar manner. They want to use mass timber as their structural system for a variety of reasons. We're seeing universities implement this. We at Oregon State University have the Wong Innovation Complex under construction. This is a building at Portland State University. And really what the benefits come down to is that a lot of the fabrication for these systems for these structural systems, the glulam beams and columns and the cross-laminated timber floors, a lot of this is done off-site. So the fabrication, the milling, all of the cutting for the connections can be done in a shop. And what that does is it removes the work from being done on site. There's no welding, there's no pouring of concrete. And so that expedites the construction process. We're able to build these buildings a little bit faster than we can with steel and concrete. And while that's great, time is always money, what that comes down to is the building can open faster. We can get rentable occupants in the spaces faster, and the building owner can make money faster. And so while we have all these incredible other benefits, it really comes down to the economics. Mass timber is also a lighter weight material than steel or concrete. So we are able to use smaller foundations for mass timber buildings. But also we live in a high seismic region here in the Pacific Northwest, and our earthquake demands are proportional to the weight of our building. So if we have a smaller weight of a building, we can then save cost on our lateral force resisting system. So we're able to really save costs on speed of construction, on the size of our foundations, on our lateral force resisting system. We're able to build these buildings a lot faster. And then, this lecture series is all about climate. And, we know that, using these natural materials is really beneficial to the climate when we look at the full life cycle assessment of these buildings. And so we can layer that on top as another benefit for this material. So with all of that, right, these materials are really primed to solve some of our major problems in the United States, particularly with housing shortage. We can get these buildings built faster. Everyone wants to be inside of the building with the exposed timber. It's a really great feeling. If you're on campus, you can go over to PV Hall and take a look and feel all the biophilia in the building. So there's opportunities to really solve some of our major building problems in the United States. But also we can use advanced manufacturing techniques and robotics to be able to fabricate these members. We're already doing that over in the Emerson lab here on Oregon State University's campus, using a ton of robotics in order to really precision fabricate a lot of the connections and a lot of these members, so that we don't have to do that work on site, so that we can have less waste in our construction process. So all of these are amazing benefits, right? It definitely shows that timber and mass timber in general is a viable building product. But we do live in the Pacific Northwest, so a lot of us have gone camping. We know that timber burns for a long period of time. It's a really great fuel. That's why we've used it for centuries. So what happens when there is a fire within this building? How can we build fire-safe mass timber buildings? How can we have it all exposed, enjoy the Portland International Airport, enjoy these buildings that are cropping up around our state, but also know that if there was a fire, we would be safe? And that's what I'm going to talk about today. That's a big challenge that we're trying to solve in our research group. So to kind of get into how we're solving this and why we're solving this, I'm going to first give you a little bit of a fire 101. There's a few different stages of fire, and fire can be characterized by the amount of energy being released, the heat release rate, and I'm going to talk about that later when we talk about the results of our tests. It can also be talked about in terms of gas temperature, the air temperature during the fire. So we are all sitting in some sort of office or home, some sort of room. So if we decided to take a match and throw it into one of our garbage cans, please don't actually do this, just imagine in your head. The contents of the garbage can would start to ignite. That ignition might grow. That fire would then ignite other things in the room, such as the carpet or the curtains or other furniture that's nearby. And as that fire grows, we would have both burning fuel as well as unburnt fuel in the space. We would start to develop a smoke layer on top of the ceiling. We would have fresh air coming into the room, and the two would be mixing together. We call that the growth phase. And that growth phase can look like what I'm showing on the screen. This is from one of our tests. We can see some smoke coming out the opening of the room. We can't see the fire itself, but we can begin to start to see what might happen there. The growth phase could also look like this on the screen, where we see more smoke coming out of this room, but yet not everything is on fire. We don't see everything on fire in this space. After the growth phase, when everything in the room is on fire, when we have ignited all the fuel in the room, we call that a fully developed fire. That might look like something like this, where we have flames actually coming out of the room. We see that almost everything in the room has combusted or is actively combusting. Now, before that fully developed fire, we call that pre-flashover, and after that fully developed fire, we call that post-flashover. The research that I do is really in that post-flashover phase. We are not looking at evacuation of occupants of the building. We're not looking at the effectiveness of sprinklers on the fire itself. Those are not going to be factors to consider in a post-flashover environment. The post-flashover environment is not suitable for humans to survive, and so evacuation needed to already take place, and sprinklers are not going to be able to help you in a post-flashover environment. That's kind of the different phases of the fire, but we have to also realize that at some point the fuel will be consumed or the oxygen will be consumed. So we had to go back to our Scout days where we think about the combustion triangle. We need ignition, we need oxygen, we need fuel. If we don't have all three, we don't have combustion. So when we lose that ventilation or we lose that fuel, we are going to hit the decay phase of the fire. The temperatures will begin to decrease, the energy in the room will begin to decrease, and our hope is that we are able to maintain the stability of the building throughout this entire curve, and we are able to maintain our compartmentation in the building. I'm sitting here in a room with Charlotte and some other people. If there was a fire in this room, we hope that none of the walls would fall down so that the fire would spread across the fourth floor of Link, and we hope that the floor wouldn't collapse so that the fire would spread downward through the building, right? We maintain the fire in that space because eventually then the fuel will run out, the ventilation will run out, and we hit that decay phase and the fire is over. So much of the knowledge that we know about fire in buildings is about a century old. And at the end of the 90s in the UK, the Building Research Establishment built a 10-story steel frame structure in the middle of a big airport hangar. They put known fuel in various areas of the building. They built out the compartments in different areas of the building, and they lit them on fire. What that did is it enabled us to quantify the fuel within the space, measure the fire demand that resulted within that space, and be able to hone in our tools to be able to quantify what the fire might be in different types of rooms with different types of ventilation, with different types of fuel. What it also enabled the research community to do is to really understand the structural response to those fires themselves. We learned and we got to quantify the large plastic deformations that we saw in steel beams and girders, as you can see on the lower right. And that showed us that there was membrane action of the slab, that this was a two-way problem. This was a three-dimensional problem, such that the entire structure was involved in maintaining that stability during the fire. We saw that there might be some damage in the connections, such as local buckling or bolt fractures, but we didn't really see collapse or failure. And what that showed us is the robustness that the steel frame building really had. So we were able to quantify, the researchers were able to quantify the fire demand in the space, then perform heat transfer analysis and understand through sensors and numerical modeling the thermal distributions through the members, and then use those temperatures to be able to understand structural performance. And a lot of that really fed into us feeling okay with the hourly fire resistance ratings that are within the International Building Code. But it also enabled us to pull together a performance-based design code for fire. The work out of the Cardington test inspired research all through the early 2000s, including my own PhD research that was stimulated after the collapse of the World Trade Centers. And between that research that went on in the United States and the Cardington research that occurred in Europe, we were able to pull together and really understand the performance of steel frame structures in fire. And be able to perform that performance-based design. But this is all for non-combustible components. Now let's go back to our Portland International Airport. This is not non-combustible components. This is combustible. So what happens now in a space where we have combustible building components? Can we take the decades and a century worth of knowledge on fire behavior and just apply it to this space? Or do we need to tweak and understand the knowledge that we already have to adapt it to be able to consider the combustibility of the timber in this space? One thing that we learned from the Cardington test and from decades of research before and after is that steel wants to expand during the heating phase of the fire and contract during the cooling phase of the fire. It can't actually do that in the buildings. That's why you see all of that local buckling, and it's because because of that restraint, you have these thermally induced forces in our steel framed structures, but we don't have that in timber. Timber doesn't want to expand during a fire or contract during cooling. Rather, the timber is charring during the fire. Very quickly, we'll see a char layer form on the outer surface of that timber, but it's not just about the charring of the timber. Beyond that charring, in that brown zone that you'll see on the screen, it's what we call the pyrolysis zone. We have what's called a heat affected area. And so when the timber is between around 50 and 300 degrees Celsius, its thermal properties, its mechanical properties are degrading quite quickly with temperature. And so we need to be able to account for that when we're trying to model this structurally in a building. So we have our char layer, we have an area beyond that char that has heated up. And this is all happening as a function of time throughout the fire duration. Right, so let's go back to our compartment. In a pre-flashover phase, I explained this a little bit already, but the picture kind of helps. When we have this burning fuel, the burning fuel is having a heat transfer reaction with the smoke layer, but also with the unburnt fuel. You'll have some radiative heat transfer between the burning fuel and the unburnt fuel. You'll have some convection and mixing between the fresh air that's coming into the compartment and that smoke layer that is up there. But also we're going to have these thermal gradients throughout our compartment boundary, where the part of the boundary that's not in contact with the fire, the outer part of the compartment boundary, is much cooler than the inside. And equilibrium is trying to be met. And so the heat is going to keep going through the compartment boundary, and we call that kind of a thermal wave. In our post-flashover environment, we're going to have those flames spilling out of the compartment. We have less fresh air coming in because the smoke layer is descending down in the compartment. But we will still have kind of this heat flux coming down from our smoke layer to our burning fuel. If we take a look at what's happening in the compartment boundary, this is exactly what's happening. Except we're going to be charring the timber as it goes through, but this is not going to be linear. Timber chars, and that char layer is actually a really great thermal insulator for that uncharred wood. And so as the char is propagating through that uncharred wood, it's not doing so in a linear manner. Now, if that compartment boundary is timber and it's exposed, meaning it doesn't have any gypsum wallboard or any other fire protection on it, that timber will ignite and also contribute to the fire itself. That timber will be considered part of that burning fuel. And there will be some radiative heat transfer reactions between the burning fuel and that compartment boundary that is on fire, and we call that irradiation. So the two will cause the temperatures in the compartment to rise. Okay, so we know what happens during that pre-flashover phase, that post-flashover phase, but that decay phase is really quite critical because that thermal wave is continuing to go through the compartment boundary. And so, there are researchers out there that might say that the timber will might continue to char during the decay phase of the fire, and that might be true. But more importantly, the timber will continue to increase in temperatures, and that results in degrading material properties and degrading structural capacity. So as we kind of decay that fire and the gas temperatures are decreasing, we are still heating up portions of the timber in the compartment boundary and reducing its mechanical properties. Now, this is going to be one of my only mentions of mass timber connections, but all of this becomes even more complicated when we talk about mass timber connections because we are mixing the materials together. We're performing heat transfer through not just the timber itself, but we're performing heat transfer through steel into timber. There's an opportunity to conduct heat up into the timber through those screws, not all the way through the depth of the screw itself, but definitely along the screw itself. In addition, we're exposing multiple edges of the timber to the fire, and each side of the timber will char at a different rate. Okay, so now that you are all experts in fire dynamics and you understand why we're doing what we're doing and all of the complexities of this problem, let's talk about what problem we specifically are trying to solve in our research. So we did a number of compartment fire tests at the Alcohol, Tobacco, and Firearms Laboratory. And what I'm putting here is almost all the other engineers and scientists around the world who have also performed these tests. Our tests are sprinkled throughout here. The left side of the y-axis is the fuel load, and the right side of the y-axis is the exposed timber as a percentage of the floor area. And what I'm trying to show you here is that a lot of the tests fall into a very singular bar that kind of are below that 600 megajoules per meter squared. Not a lot of tests have a lot of exposed timber above 200% of the floor area, and not a lot of tests use large amounts of fuel load. And the reason that's important is going back to our compartment fire figures. When you have exposed timber, you could be exacerbating the fire itself. And if you have a high fuel load, that could be even worse. So if we break this down into a table, what we see is that actually very few of these tests fall into that high fuel load area. And the majority of those tests, and almost all of those tests, don't use actual modern furniture. And the reason for that is, modern furniture, when you burn, is expensive. But the result is that the dynamics of the fire itself may not represent what might occur in real buildings today. By using wood as proxies for furniture, we are changing the composition of our fuel. We're substituting cellulose-based fuel for synthetic fuel. So using, wood burns very slowly. It burns for a very long time versus, the type of chair I'm sitting on right now might ignite very quickly and not burn for very long. It might be completely burned in a short period of time. And if we kind of extrapolate that to an entire room or entire building filled with furniture, that would change the dynamics of the fire quite a bit. So what we aim to do is to really get at how do we holistically evaluate mass timber buildings in fire, considering all of the performance objectives that we need to put onto our buildings, which is becoming more and more every day. And so it's really hard to kind of juggle these performance objectives. But in order to get to fire-safe mass timber buildings, we need to be able to actually quantify and calculate the fire demand that is within these buildings. That's going to depend on our building occupancy, the geometry of our compartment or our rooms. That's going to 100% depend on our fuel characteristics and the thermal properties within the space. When we can actually quantify what the hazard is in the space, the fire hazard in the space, we can then perform our heat transfer models. We can then understand how quickly we are charring the wood, how quickly we are moving that thermal wave through the timber and then degrading those structural and material properties, and relate that to our structural capacity in our structural model. So able to actually calculate what the structural capacity of our members are and our building is during different fire scenarios, we have to first and foremost be able to quantify what that fire scenario is. And then we can couple it with our sustainability and emissions practices. Typically, when we do a life cycle analysis of a building, we're looking at the global warming potential of the materials, or we're looking at the carbon content of the materials. If we include a hazard within that life cycle assessment, such as an earthquake, for instance, we might consider the carbon cost of repairing that building. Now, when we have a fire, we actually have emissions to consider as well. And so what are the emissions of a building, and what's that trade-off when you have exposed mass timber versus encapsulated mass timber when you have gypsum wallboard? Gypsum wallboard is going to add more carbon to your building, but is going to prevent the timber from burning. It might off-gas, and it might have emit worse products. We don't know. And so we have to consider all of that within our holistic evaluation of our mass timber buildings to be able to make informed decisions about which way to go. So with that, I'm going to talk about now the bulk of what we did. So we tested four compartments across 3 different buildings. The way we did that is tests 1 and 4 were consisted of the same building, and we fully encapsulated that building. So gypsum wallboard was on every single surface of the interior of the structure, so the timber was not damaged. Test 2 consisted of every surface being exposed. We used no encapsulation in that structure. And then test 3 only had encapsulation on the long longitudinal walls. There was an opening at the front of the compartment, and there was a glue laminated timber frame in the middle of the compartment. You can see all the dimensions that are on the screen here. Tests 1 and 4 were exactly the same. The only parameter that changed between these two is the fuel. So we tested test number 1 with furniture and modern fuels. And test number 4, we used wooden cribs that would equate to the same fuel load if we were going to calculate that out. And then we tried to place the wooden cribs in areas that we did have the fuel in test number 1. Right? We didn't know how controversial the squishmallow burnings would be at the beginning of these tests, so I apologize, everyone, for who has kids and are watching this at home. For tests number 1, 2, and 3, those had the exact same furniture in every single test in the exact same location. The only thing that changed between tests 1, 2, and 3 are that the amount of encapsulation, where you can see test 1 on the left, full encapsulation, gypsum wallboard on every single surface. Test 2, no encapsulation, and test 3, only on those long longitudinal walls. Now you're going to see, you probably see something in the back corner between the back wall and the ceiling. Those are different connections that we tested within our compartment to look at how different connection configurations and the amount of fire protection on these connections might perform in a natural fire environment. I'm not going to talk about that today as there's not enough time to cover all of that. So what were some of our research objectives? When we were looking within each compartment, we wanted to know what was the temperature distribution from the floor to the ceiling. Was it fairly uniform? Was there big differentiations between that vertical temperature distribution? We wanted to know what the temperature differences were between the front of the compartment as well as the back of the compartment. We had that glue lamp frame in the middle of the compartment, and we were really curious how that affected the fire itself. When we're comparing between the compartments, we wanted to look at the effect of encapsulation on temperatures, on char rates, and on our heat release rate, on energy being released by the fire. And then lastly, we really wanted to know about the effect of using furniture versus wood cribs on all of these factors as well. There are a lot of researchers throughout the world, and there's a lot of research that has occurred using wood cribs. However, our current furniture is not really cellulose-based anymore. It's really synthetic. And so we really wanted to know and test whether we could extrapolate the results from those tests to modern fuel load and modern fuel environments. Okay, so we had about 800 instruments throughout the entire compartment, and there isn't enough time left in this lecture to go through all of it. So I'm just going to go through some of that here. All of these red dots, this is a plan view of the compartment. They represent what we call thermocouple trees. What that means is these are these strings that we dropped from the ceiling to the floor, and we put thermocouples at about 0.6 meters or about 2 feet from the ceiling to the floor. This allows us to collect a thermal distribution of throughout the compartment, throughout the front and the back of the compartment, but also from the floor to the ceiling as well. We used the thermocouple that was 0.6 meters below the ceiling. When that thermocouple reached 600 degrees Celsius, we said that meant at that point we had reached flashover. So we can actually quantify that flashover point so that we can differentiate between pre-flashover and post-flashover. All right, so we're ready for some results. So this is a plan view of the compartment. It's kind of a cartoon of the compartment with all of the furniture. In the back of the compartment, we have our Squishmallows and we have our couch. We have a computer, we have some toys. In the front of the compartment, we have a bunk bed. That's what that white rectangle is. And then lots of clothes and shoes, because everyone always has clothes and shoes all over the place. And then we have a desk with a computer. We have a sink. We had some cleaning supplies below that sink. So lots of different types of fuels throughout the compartment. In every single test, we put the ignition in this location. So it was in the back left corner of the compartment in the couch, and we ignited in the same way every single time, even with wood cribs. It was the same way every single time. The fire ended up spreading and igniting around the back of the compartment, and then it moved to the front of the compartment, and then it moved back to the back of the compartment. And we know this because we had some cameras in the space and we could see it before the cameras burned. It's hard to do fire testing because of the harsh environment. And we can also see that in our data. And I'm going to go through a bunch of our data with you all today and show you exactly how we can see this. And it really helps to pull the data all together. So if we begin to just compare test 1 to test 4, just in our maximum heat release rate, the maximum amount of energy that's being released by this fire, what we can see is that the maximum heat release rate decreased when we went from using modern fuels to wood cribs. But more importantly, the time to that maximum heat release rate increased by about a factor of 3 when we went from modern fuels to our wooden cribs. So again, wood burns for a really long time and it burns slowly. And that was really reflected in our time to maximum heat release rate here. So we could see that. And we can see it show up in the data. When we go from test 1 to test 2 to test 3, what we see when we're adding that encapsulation is that as we add more encapsulation, we are decreasing our maximum heat release rate. When we go from test 1 to test 2, we actually decrease that time to the maximum heat release rate, right? So we get to that maximum heat release rate very quickly. But more interestingly, when we add encapsulation on those longitudinal walls, we decrease our maximum heat release rate, our maximum energy released just a little bit because we're also decreasing the amount of fuel, but we get there faster, which is really interesting. And that's going to come up a little bit in some of the other data that we're going to look at. So I'm about to show you some plots, and don't be too overwhelmed. I'm going to walk you through them. So what I'm showing you here are temperatures. The gray is 0.6 meters below the ceiling. The hatching is 0.6 meters above the floor. On the left is test 1. On the right is test 4. Test 1 has furniture and modern fuels, and test 4 has wood cribs. And this is just for the front of the compartment. There's a little cartoon in the upper right-hand corner that tells us if we're looking at the front or the back. So right off the bat, we in test number 1, we had a shorter time to flashover. So that kind of reflects our time to maximum heat release rate. The x-axes in these are different because we had to cut test 1 short. The encapsulation failed because of an installation snafu. The bigger difference is that the temperatures were actually a little bit higher in test 4 than they were in test 1. It took longer for the test number 4 to reach its peak heat release rate. It had more time in that burning and that combustion phase to that peak heat release rate. So that all of that resulted in higher temperatures in the front of the compartment. Let's put some lines on here though. So what we can see is that our time to flashover and time to peak heat release rate are very close to one another. In test number 4, then we had sustained combustion followed by a decay phase. But in test number 4, we had more differentiation between our time to flashover, our time to peak heat release rate, kind of this longer sustained combustion, and then we hit a decay phase. In the back of the compartment, the ignition is in the back of the compartment. Just as a reminder, we see these spikes followed by a decrease in temperature, right? So we hit flashover, and then the fire actually moves to the front of the compartment. The combustion occurs in the front of the compartment. Finally, there's enough oxygen for the back of the compartment to continue combustion, and the fire moves to the back of the compartment and combusts in the back. And so we are able to kind of discern what's going on with the fire movement in the space from all of our data. However, in the back of the compartment, we actually see our time to flashover with the wood cribs as faster than the test number 1, from test number 4 to test number 1, and that's the opposite in the front of the compartment. So if we begin to compare test 2 and 3, so as a reminder, both had modern fuels. Test number 2 was fully exposed. Test number 3 was partially encapsulated. What we see is test number 3 has a faster time to flashover. It had a faster time to peak heat release rate as well. And we can see that in our lines. In both cases, that time to flashover and time to peak heat release rate are very close to one another. But then we just have sustained combustion because the CLT is burning. We've burned all the fuel in the compartment and the CLT began to burn. Both tests never hit a decay phase, and we had to actually cut the tests short because the compartment was about to collapse in both cases. So this is for the front of the compartment. In the back of the compartment, we begin to see kind of very similar behavior to test 1 and test 4, where we see those spikes where we have our time to flashover, our peak heat release rate. We then have a decrease in temperature as the fire moves to the front of the compartment. Fire comes back to the back of the compartment. We have sustained combustion until we stop the test. And very consistently with the front of the compartments, test number 3 has a higher time to flashover by about a minute than test number 2. So the last part that we will begin to compare with one another are the char rates between just test 2 and test 3. So we're going to start with test 2. We're going to look at some plots first. If we focus only on the front of the compartment, the red line is the gas temperature closest to the wall that we're looking at. And what I want you to focus on is that you see these dotted lines and they all kind of shoot up. And as we move along in the plot, what the slope changes. Each of those lines corresponds to a thermocouple, a temperature sensor that's embedded in the CLT wall. And so back at the beginning, we talked about char rates. We talked about how it's not linear. And you can see it in these plots here, that we are actually not charring the timber in a linear fashion as we move through that depth of the wall. And we can see that in the back of the compartment too. But what we see here is we see that spike in the temperature, right, that we saw in our previous plots, the decrease in temperature because the fire moves to the front. And then when combustion begins back at the back of the compartment, we begin to see the charring of the wood, right? So we see this kind of delayed charring between the front and the back, which is really interesting to see. And it tells us a little bit more about the fire dynamics within the space. And here, so we can see the char rates there. We can plot this in a different way such that we can look at the char depth versus time through all of the members in test number 2. The back wall, the ceilings, the front wall, the side walls, all of them. Those lines are the char rates from our codes, from the codes within the United States as well as in Europe. The dots below these lines are char rates that are slower than the prescribed code char rates, and those tend to be in the back of the compartment. The dots above the line are char rates that are faster than our prescribed char rates, and those are in the front of the compartment. So again, this is just another way of visualizing the data to show that we were combusting in the front much faster than we were in the back. When we look at test number 3 with our partial encapsulation, we can see the same thing. These are just the ceilings. And so what we can see here is, again, that delayed charring from the front of the compartment to the back of the compartment. We can see the changing in slopes, as well as the spacing between the lines themselves. So we're not charring at a linear fashion. And we see that in our plots here. This is our char depth along the vertical axis versus our time, where we see our charring slower, very few points that were slower than our code prescribed char rates. And then a lot of points are above that, going faster than our code prescribed char rates. When we compare them to one another, what we see is that we see a lot more nonlinearity in test number 3 than we do in test number 2. So we see this, we saw these different fires that resulted in these two compartments to one another by just adding that encapsulation on those longitudinal walls. We see that there's increased charring in test number 3 as compared to test number 2, even though the maximum heat release rate in test number 2 was a little bit higher. All right, so wrapping up, what are some of our conclusions? Well, when we look at the effect of our fuel composition, we are seeing that the fuel composition has a huge impact on the fire dynamics within the space. We're seeing a little bit higher temperatures, but actually lower peak heat release rates and much longer times to those peak heat release rates. So using these wooden cribs in these environments might inform information about fire dynamics in general, but it cannot be extrapolated to our real building scenarios. When we look at the effect of encapsulation, we're seeing that it does have a big effect on the maximum temperatures. It didn't have a big effect on the maximum temperatures, but it did on the maximum heat release rate, on the time it takes to get to that maximum heat release rate, on the time to flash over, as well as our char rate. So adding those encapsulation layers really changed the fire within the space because we are beginning to cover up some of the fuel that's the timber itself. And then lastly, our last conclusion is really that no one of these parameters can really define the fire itself. We can't really define the fire in our time to flash over, or our maximum temperature, or our peak heat release rate. We have to really look at all of this together to really understand what's happening in the fire dynamics within that space. So where are we going with all of this next? Well, we are going to continue to crunch a lot of our data and validate a lot of our numerical models, and to be able to simulate that fire within a mass timber space, so that we can actually perform heat transfer analyses on our timber products and timber elements, and then perform that structural analysis. We are still working on crunching the data from our emissions, so that we can actually go and pull this together in a life cycle assessment of mass timber buildings, considering fire and considering the emissions from those fires. So I really do want to thank all of the funders for this research that made it possible, as well as all of the incredible collaborators. If you want to know more, here is the website for the project that I talked about today. The last point that I'm going to make is that something really exciting is coming to OSU at the end of this calendar year, and we are building a fire lab, the Oregon Fire Testing Laboratory. It's right next to the Emerson Lab, right on OSU's campus. The ground has already been broke for this project. It is well under construction, and we would love to have industry partners, whether it's local or abroad or throughout the United States. So if you're interested, please let me know. And thank you very much. I'm excited to take some questions.
Thank you, Professor Fischer, for sharing your research with us. I thought that was really, really interesting. I feel like in classes we don't really learn a lot about wood materials. We learn a lot about steel materials. I just thought that was so fascinating. I had one quick question. I was really curious about how in test 2 and 3 they never reached the decay phase. Is that because of the material that's used to seal exposed timber? Or is it just because there was nothing to seal that material?
Yeah, so in test number 2, there was no fire protection within the compartment. We did use fire caulking, so that flames were not coming out of the compartment itself. But basically, you really only hit that decay phase when the timber itself is not contributing to the fire. And so when the timber has charred a little bit, but you're not really contributing to the energy that's being released by the fire, you will be able to hit that decay phase. But in those 2 tests, we began to combust the mass timber, this cross-laminated timber and the glue-laminated timber itself. And so we had consumed all of the what we call movable fuel in the space, which is all the furniture and the modern fuels. And now we were using the physical structure. The fire was using the physical structure as the fuel. And so it just continued to burn. And it would have continued to burn until the whole thing collapsed.
Interesting. We will now begin the Q&A portion of our event. Remember, if you'd like to pose a question for Professor Fischer, please submit it using the Q&A button at the bottom of your Zoom screen. We also had some advanced questions submitted by audience members. We won't be able to address every question today, but we'll get to as many as we can. One pre-submitted question we had was, does charring on the exterior of mass timber members under fire conditions differentially impact connections despite the members' overall structural resilience?
So I'll try to discern what the person meant by this question. When mass timber connections are exposed to fire, we will, depending on what is exposed within the member. So if you have some exposed screws, which is actually quite common, then you might conduct heat up into the connection. when you do char the exterior of mass timber members, you're reducing the cross section of that member to actually resist those structural loads. So you have less depth and you have less width to resist those structural loads. And so you need to be able to consider that within your calculations. Now, where all of the heat transfer comes in is if you have quite a complicated connection, you might be degrading portions of the timber itself. So for instance, you might have a reduced withdrawal capacity of your screw because you don't have that full length of screw embedded in your timber anymore. It's charred some, or it's the structural capacity of the timber has degraded. So you kind of have to work through all the individual failure mechanisms to see how you can then recalculate the capacity of your member after a fire.
What are the key differences between mass timber and steel in fire conditions, particularly regarding fire behavior, structural performance, and residual load-bearing capacity?
Sure, there are a lot. So from a structural engineering perspective, steel is very fascinating during a fire. We have all of these thermally induced forces that we don't design for at ambient temperature. So all of that, expansion that the steel wants to do during heating, and then the retraction it wants to do during cooling, we don't actually design our connections or our members for that at all. And so that's one of the biggest differences between steel and timber during a fire, is we don't really have that thermal expansion and contraction in our timber during a fire. Now, the other side of the coin is that quantifying the fire demand in a space that has a steel structure is a little bit easier than in a space with any exposed timber. And that's because your boundary conditions are not combustible. They're not contributing to the fire in that space, versus mass timber space such as PV or the Portland Airport or any of our other mass timber buildings. The timber is going to be part of the potential fuel for the fire itself. So quantifying the fire demand becomes a bit more complicated.
Interesting. What are the implications of what you are finding for the mass timber industry in Oregon?
Sure. So there is very little fire research on mass timber within the world. This is kind of a new topic that has come out that people are ramping up in doing over the last decade and a half. Being able to have data on mass timber structural performance during a fire, or just mass timber compartment performances during a fire, is really helpful for the mass timber industry. I truly believe that once we know our hazard demands, we can actually design for them. So we need to be able to know what the problem is, or where the material really thrives, so that we can actually take advantage of that in our design. And so being able to do that locally is really special.
Nice. I actually have a follow-up on that. Do you think, I know mass timber is really popular right now, do you think we are moving too fast in the mass timber construction design without this research that is not fully completed?
No, most of what is actually being built out there is actually code compliant. Mm-hmm. So I know we see a lot of exposed buildings out there with not a lot of fire protection, but it is allowed by the International Building Code. And so there aren't a lot of buildings that are being built beyond the code level adoption. And that would mean very tall timber buildings here in the United States. And a lot of the reason for that is because a lot of our timber buildings are being built in the West, where we have earthquakes, and we can't really build tall timber buildings like they do in Sweden or Norway, because they don't have earthquakes there. We have them here, so our buildings are going to have to be designed for that. And I think that we are moving towards an area where we are actually mixing our materials really well together. So, before I came to Oregon State University, the industry was really divided up in, it's a steel building, it's a concrete building, it's a timber building. But now we're dealing with these buildings that have all of them. We're using materials where it makes sense and where they can shine in their strengths. And that results in very efficient use of materials, that results in less waste in materials and over design. And so I think the emergence of mass timber is actually forcing us to be more efficient in our designs and to really think about why we're using different materials in different ways.
Nice. If you know, is there a list of contractors that are proficient in constructing with mass timber? Are the systems simple enough that any experienced contractor is able to easily learn how to correctly implement it?
So that is a great question. That question depends on the size of your building. If you're looking to build a glulam carport, you can use any sort of residential contractor. If you're looking to build something like PV Hall or the Emerson Lab or the Wang Innovation Complex, where you're building these more commercial mass timber buildings, there are contractors that are proficient in that. Timber Lab and Swinnerton are two examples of that. There are many other contractors as well, and actually in the Pacific Northwest, we are very lucky to have a carpenters union that is actually actively training new carpenters on how to use this material. And a lot of the times they do so actually with us here at Oregon State University. So a lot of our large scale tests they are engaged with, and we are working side by side as engineers and contractors to really see how to best build these structures.
Nice. Have you already or are you planning to test the structural strength reduction for structural columns and beams during fires? Which building material performs best?
I have not done any post-fire testing of mass timber. I typically test all the way to as much to failure as I possibly can when I'm testing in fire. I want to know what the failure mechanisms are so that I can actually prevent that from happening in the designs. I have done post-fire testing of steel, and there is a lot of post-fire testing of concrete out there as well. There's a lot of literature on that, but there is very little literature on post-fire testing of timber.
Nice. We have time for one final question. Is there anything else we should know about the new Oregon Fire Testing Laboratory? What tests will the fire testing lab be able to run?
Great question. This laboratory will have the capacity to do furnace testing as well as open burn testing. The test that I showed today had maximum peak heat release rates of just under 10 megawatts. We will have a 3 megawatt hood, so we can't do those types of tests, but we could still do tests of about the size of a 12 by 12 garden shed or a car. So those types of tests we could be doing inside the laboratory, as well as furnace testing, so that we could actually be loading our structural components. So stay tuned.
Nice. Thank you again, Professor Fischer, for the fascinating lecture and for your answers to all our questions. Before we go, do you have any parting comments to share with the audience?
No, just thank you so much for having me, and thank you, Charlotte, for being such a great moderator.
Thanks everyone for joining us today and for your great questions. As a reminder, we will email you a captioned video recording of the lecture. We also hope you'll join us for future College of Engineering events. Thank you again for attending and have a wonderful afternoon.